This might have all sounded a little bit dry so far, so let's become much more concrete. So before delving into the mathematics of signal processing, we are going to construct a simple motivating example. The way to do this is we are going to look at simple operators like sums and multiplications and delay elements that we're going to build together to build, for example, a moving average or a recursive filter. The recursive filter, it turns out, is exactly what happens into your bank account, assuming you have some money left. After we have these simple operators, we are going to build a music synthesizer based on the Karplus strong algorithm and actually going to listen to some computer music. Before delving into the mathematics of signal processing, let us do a simple and motivational example. We will see that there are simple primitives that can be used to build interesting signal processing devices. After building up the basic blocks based on usual notions like averages, moving averages, and bank account returns, yes indeed, we shall construct a simple music synthesizer known as the Karplus strong algorithm, and then listen to it. The menu is therefore the following. First, we look at digital signal processing as Lego blocks. So we'll see fundamental building blocks and how to put them together. From there, we go to moving averages, which is an extension of the usual averages that we all know. Then we shall look at recursion, and the best way to learn about it is to revisit your bank account and how your wealth goes up and down depending on returns. With this example in hand, we can build a simple recursive synthesizer. Once built, we can actually listen to actual sounds. Okay, so let's think as digital signal processing as a Lego set. So you have blocks, various colors, various shapes, but they all fit together, as seen on the left side. On the right side, you see a block diagram of a basic signal processing device. This will turn out to be a filter, but this we'll see later. You can see there are blocks, there are arrows, there are adders, there are multipliers, and so on, and an input xn, a sequence of numbers, gets transformed into yn, another sequence of numbers. So, what is a basic building block like an adder? It takes two signals, two sequences, x and y, adds them together, x plus y. In a diagrammatic forms, we see two signals at the bottom left. Added together, they add to a constant, because one goes down linearly, the other one grows linearly. How about the multiplier? It is denoted simply by a variable, in this case alpha, that is put next to an arrow. So x gets transformed into alpha times x. Again, an example, we have the same descending signal multiplied by 1/2. It has the same shape, but it is scaled by 1/2. The delay is denoted by z minus 1. We will see why this notation shows up later, but for now simply think that a sequence xn is shifted in time, shifted to the right, therefore it is denoted as x of n minus 1. Again, we take our usual signal, the descending linear signal, and shift it by 1. Sure enough, instead of starting at the origin, it will start at time instant number 1. If we know how to delay by 1, we certainly can also delay by n. This is denoted by xn becoming xn minus capital N. Let us look at our usual signal and delay it by an integer n is equal to 4. Now, instead of starting at the origin, it will start at the integer n is equal to 4. Now that we have building blocks, let's create some operators. The first operator we shall look at is the average, or the simple average that everybody is familiar with. For example, in Switzerland, the average number of children per woman is 1.42. You probably had to worry about the infamous GPA, grade point average. Here we are concerned about moving averages. That is, we compute a local average of a sequence as we go along. The simplest case is a 2-point moving average, denoted by xn plus xn minus 1 divided by 2. So we take two neighboring samples of a sequence and we take their average, which now will change over time as it depends on n. We can build this using the Lego blocks from earlier. So on the left we have the input xn, it is delayed by z minus 1, it is added and then multiplied by 1/2 to result in the moving average yn is equal to xn plus xn minus 1, the sum divided by 2. Let's look at this. For a very simple signal, this is the delta sequence, which is equal to 1 at the origin, 0 everywhere else. The moving average will be 0 everywhere except at the origin and at location 1, where it is equal to 1/2. Another typical signal is the step sequence, which is 0 for negative time, equal to 1 for n is equal to 0 to infinity, denoted by un. What will the moving average look like? For negative indices, it will be 0. For 0, it will be 1/2, because it's the average of 0 and 1. For 1, it is the average of 0 and 1, so it is equal to 1, and ever after, it is equal to the constant 1. If we take a more complex signal, like a cosine function, cosine omega of n, where omega is picked here as pi over 10, then you can see the signal on the left and its average on the right. It doesn't seem to have changed very much. If you look carefully, you will see that the zero crossing at n is equal to 5 has disappeared because of the moving average, but the basic frequency, as we shall discover, is actually still present. It is pi over 10. Now if we take a very high frequency, omega is equal to pi. So cosine of omega times n, or cosine of pi times n, this sequence is alternating between +1 and -1, as you can see on the left side. If we take the average, nothing comes out, because every time you take an average, it's the average between plus and -1, which is 0. Therefore, here we have a very different behavior from the previous cosine, since an input that is different from 0 is resulting in an output that is exactly equal to 0. Now, a natural question will be, what if we reverse the loop of the moving average? So let's look at the block diagram again and turn around the arrow. Instead of going forward, going backwards, still with a factor alpha and an adder. This turns out to be a very different object. At first it looks very similar, but it will be obvious that a single input different from 0 will in general generate an infinite output, which is certainly not the case of a moving average. To study this, we will go back to something we are all very familiar with. It's a simple equation that will describe the value present in your bank account. Let's assume the following things. You have a constant interest rate of 5% per year. Assume you put or take money only once a year on January 1st. Interests for a positive balance or charges for a negative balance are calculated on December 31st. They are added January 1st of the following year. So call xn the input, adding or subtracting from the bank account on January 1 of year n. Call yn the content of your account on December 31st of year n. Then it is not hard to see that yn is equal to 1.05 yn minus 1, that is the 5% either borrowing rate or interest rate on the content of your bank account the previous year, plus xn, which is what you put in at the 1st of January of the year. This recursive equation can be depicted in a block diagram as shown now. So xn enters, it is added to 1.05 the previous content, which is y of n minus 1. This is a feedback loop with a delay element z minus 1. This added together indeed gives the output yn. So, to make clear, yn is equal to 1.05 y of n minus 1 plus xn. Let's look at a few examples. Let's take a one-time investment. So xn is equal to 100 at time 0 and 0 everywhere else. So we can calculate this by hand just to get the feeling. Y of 0 will be equal to 100, because that's what is put into the account. Y of 1 will be 105, Y of 2 will be 110.25, that's 1.05 squared times 100, Y3 is something of the order of 115, and so on. If we depict this, then we see that your wealth is slowly increasing. Actually, not that slowly, because it will turn out that it's actually an exponential. So in general, yn is equal to 1.05 at the power of n times 100. Let's look at the second example. Let's take a saver. So the saver puts 100 every year after the origin of time, that is 0. The solution to this difference equation is not obvious. We will be able to write it down after we have learned some basic tools about difference equations. But we can calculate a few points. So y of 0 is 100, y of 1 is 205, y of 2 is 315.25, y3 is of the order of 430, etc. So we can plot this, and now we see that it's something that goes faster than the linear growth. Why? Because there is compound interest. The result of the different equation is yn is equal to 2000, open parentheses, 105 to the power n plus 1 minus 1 u of n. Let's look at the third example, the independently wealthy person. So xn obtains the following way. You put 100 at time 0, and then you take the interest out every year. So the interest is 5%, so 5% of 100 is 5, and we have 0.5 times un minus 1 that comes out. The interesting thing is that now the output keeps constant. It's 100 at time 0, this we know, that's what we put in, and then when we thought it went up to 105, we take out 5, and so it stays at 100. And so the output is perfectly constant from 0 to infinity. We can now generalize this a little bit. We put a delay by capital M, and we put a factor alpha. So yn is equal to alpha times yn minus capital M plus the input xn. We are engineers, so we like to choose alpha smaller or equal to 1. This is quite different from economists. We had just seen the previous examples where alpha was 1.05. Let's make an example. Let's take m is equal to 3, alpha is equal to 0.7, and as an input, our usual signal, which is equal to 1 at the origin, 0 everywhere else. We can calculate easily what's going to happen. For the first instant, y0 is equal to 1, then it is 0 for 2 instants, then it's equal to 0.7, etc. If we plot this, we see something that looks almost periodic, namely of period 3, except that it decays slowly as a power of 0.7. If we put a more interesting signal, that's a little ramp here, which starts equal to 1 at 0, equal to 2 at 2, equal to 3 at instant 2, and we put it as an input, then we truly see the repetition. So alpha here was chosen equal to 1, so there is no decay in the signal. It simply repeats one period, this period from 0 to 2. Therefore, we have seen that the m-tap delay essentially generates an m-sample periodicity. If we want to play music with this, we need to associate a time period, capital T, to sample intervals. The periodic signal of frequency f will be, in hertz, a frequency 1 over capital M times capital T. So for example, if T is equal to 22.7 microseconds, M is equal to 100, then the frequency that is generated will be of the order of 440 hertz. Let us look at this. So for example, if we want to play a sine wave, M is equal to 100, alpha is equal to 1, xn is equal to 1 period of a sine wave, sine of 2 pi times n over 100, and then this will be nicely repeated by our recursive loop and generate a sine wave that is indeed equal to a 440 Hz sine wave. Let us now listen to a sine wave of frequency 440 Hz. So we have seen that M controls the frequency, or what's called in music the pitch. To imitate the violin, we need to go beyond a single sine wave. A crude approximation is a triangular wave. We can change the pitch by changing M. We can simulate the decay by choosing alpha smaller than 1. Let's look at an example. M is equal to 100 again, alpha is equal to 0.95, xn is 1 period or a zero mean triangular wave. Sure enough, if we put this into our recursive loop, it will generate a sequence of triangular waves that slowly decay with 0.95 to the power of the number of periods. Let us now listen to this sawtooth wave with the decay given by 0.95 to the power of the number of periods. We are now at the Karplus strong algorithm. This is an algorithm that was invented in the 80s to simulate guitar sounds, and what is very particular is that it's not initialized with a sine wave or a triangle wave, but with a sequence of random numbers. So we see an example here where M again is 100, alpha is 0.9, that gives a relatively slow decay, and xn, 1 period, is actually a set of random numbers. We can change the pitch again by changing M, and the decay depends on the factor alpha as usual. We see now what signal is generated, and we are going to listen to exactly this signal with various pitches, and you will see that this is a crude imitation of a guitar sound. Let us listen to the output of the Karplus strong algorithm. So it is initialized with random numbers, 100 of them, and then there is a decay of 0.9, and we can listen to this. It should sound like a plucked string. Of course, it's a coarse approximation, but now we can listen to it. Let us wrap up this example of building a synthesizer. We have seen basic elements, adders, multipliers, delays. We have seen two systems, moving averages, as well as recursive systems. We were able to build simple systems with interesting properties, and now we want to understand these in more details. To understand this, we will need a mathematical framework, which is the topic of the next lecture.